Suppose we add several waves together to create a new wave. If we change the amplitudes of the waves, the resultant wave also changes. The waves can have different wavelengths. The bottom wave has a slightly different wavelength than the other two. As we move the two other waves, notice how the sum of all the waves changes. The resultant pattern moves at a different speed than the original waves. We refer to the speed of each original wave as the phase velocity. We refer to the speed of the resultant pattern as the group velocity. When we have a wave describing a quantum particle, it's the group velocity that determines the velocity of the particle. Any wave function can be thought of as the sum of waves of many different wavelengths. For a quantum particle with mass, such as an electron, the waves with a shorter wavelength have a faster phase velocity. For classical water waves on the surface of an ocean, the waves with a shorter wavelength have a slower phase velocity. When different wavelengths have different phase velocities, we can have dispersion, where the waveform has a sharp peak at one moment in time, but is dispersed at another moment in time. On the other hand, if all the different wavelengths have the exact same phase velocity, then the pattern can stay constant, and the group velocity will be equal to the phase velocity. Examples of waves where all the different wavelengths have the same phase velocity are electromagnetic waves through a vacuum and waves on an ideal string. If we have waves with the same amplitude and speed, but moving in opposite directions, then we produce what we refer to as a standing wave. Much more information about waves is available in the video Waves, Light, Sound, and the Nature of Reality, and in the other videos on this channel. Please subscribe for notifications when new videos are ready.